Throughout this unit, we've talked about one-dimensional collisions and two-dimensional collisions. We've talked about collisions in which the objects stuck together and didn't stick together. We've talked about T-bone collisions and glancing collisions. There's all kinds of ways that we can classify collisions. But the main way that collisions are actually classified is not by whether they stick together or not. It's not by whether they glance off of each other or hit each other at 90 degrees. It's not whether it's one-dimensional or two-dimensional. The main way we classify collisions is by calling them either elastic or inelastic. Now, it doesn't matter what type of collision we have, whether it's elastic or inelastic collision. Momentum is always conserved if it's an isolated system, right? What's an isolated system again? No external forces. Good. That's what you're going to say? Good. No external forces. If it's an isolated system, momentum is always conserved. So look, momentum is conserved. If it's an elastic collision or an inelastic collision, well then, what's the differentiation? What makes an elastic collision different than an inelastic collision? It's not momentum, it's kinetic energy. If it's an elastic collision, then kinetic energy is also conserved. If it's an inelastic collision, kinetic energy is not conserved. In other words, kinetic energy would be lost in an inelastic collision. Now, the reality is most collisions that we see in the real world are inelastic. Momentum is conserved, kinetic energy is not conserved. So I'll tell you what, if you got to guess inelastic. You're probably going to be right 80 or 90% of the time if you guess inelastic. Now, we want to avoid guessing if we can, because I don't want to be right 80 or 90% of the time. I want to be right 100% of the time. So try to avoid guessing. But if you have to, guess inelastic, because you still got a pretty good chance of being correct on it. How do we know, rather than just have an 80 or 90% chance of guessing correct? How do we know that we're correct? Well, if two objects stick together, we know that kinetic energy will be lost every single time. So if object number one hits object number two, there's Velcro, whatever, they entangle, they go off as one, kinetic energy will be lost. This will be inelastic, 100% for sure, 100%. Every single time, kinetic energy will be lost. We don't even need to calculate it. Kinetic energy will be lost. If you calculated it, you would find the final kinetic energy is less than the initial kinetic energy. If they bounce apart, well, you know what? It's likely inelastic still. It's likely inelastic, but we don't know for sure. It may be inelastic. Well, it probably is. It may be elastic. But it's probably inelastic. It's not for sure. But you know what? If in doubt, guess inelastic. I'm not telling you, though, that if they bounce apart, that you should automatically guess inelastic. Right? Figure it out if you can. But if in doubt, guess inelastic. How do you figure it out? If they stick together, you don't need to figure it out. If they bounce apart, you do need to figure it out. Figure it out by calculating the kinetic energy. Right? You know how to calculate momentum, calculate kinetic energy by saying 1 FmV squared, right? Difference is, man, calculating the kinetic energy before and after is easier, way easier, because we don't have to worry about signs, positive, negative. We don't even have to worry about like 74 degrees south of west. Why do we not worry about direction? Because kinetic energy is a scalar. Momentum isn't. We see a funny angle. We don't like funny angles. We have to do our x and y components and so on. One is moving to the north, one is moving to the south. We've got to pay attention to positives and negatives. But when we're dealing with kinetic energy, we don't, because kinetic energy is a scalar. Calculate EKI, calculate EKF. If EKF is less than EKI, it's inelastic. By the way, what is it if EKI is less than EKF? In other words, you gain kinetic energy. What is it now? If you find that the final is more than the initial, what is it? Wrong. That's what it is. If you find the final kinetic energy is more than the initial kinetic energy, you've made a mistake. It'll either be the same or less in the context of a collision, right? Now, an explosion, you could gain kinetic energy, but we don't classify those as inelastic or elastic, okay? So if the question says this is elastic or inelastic, and you get that you gained kinetic energy, you've made a mistake. Do it again, okay? So if they stick together, don't bother doing the calculation. You know it's inelastic. If they bounce apart, you know what, it's probably still inelastic, but you should do the calculation to check. But if you're having trouble with the calculation and you got to guess, what should you guess? Inelastic, because it's most collisions are inelastic. How come? Why are most collisions inelastic? Yeah.
It's usually not like an accelerated system so much.
No, not so much that. It's a good guess, actually, but not so much that. You guys learned in Science 10 about the second law of thermodynamics. Says basically that when you have an energy conversion taking place, you always lose a little bit. Remember that? Vaguely remember that? When you convert energy from one type to another, you lose a little bit of energy. Well, picture this. A basketball hits the floor. Okay, forget about the conversion of energy from potential to kinetic as it falls. Just look at the collision itself. When a basketball hits the floor, what does the basketball do? Squishes, right? So in other words, you have kinetic energy that's converted to elastic potential energy. And then as it bounces back, elastic potential is converted back to kinetic, right? You have two conversions that just took place. Well, if you have conversions of energy that took place, you must have lost some energy. But then you're going to have less kinetic energy after than you had before, right? Does that make sense? The only time we really don't have any conversion of energy taking place is when things that won't compress, that won't squish, hit each other, like subatomic particles. Right? Even to 2 or 3 decimal places, probably like billiard balls. They don't compress very much, right? A little bit, but to 2 or 3 significant figures, probably not. We might find that those are inelastic as well. But for the most part, elastic. But for the most part, we're going to find when two things collide, there is some compression. We do lose a little bit of energy, and therefore it's got to be inelastic. Okay? Most things do compress, and that's why most things would be inelastic rather than elastic. All right, let's do an example. We have 2 examples, but let's skip the first one because you can do the second one. You can do the first one for sure. There's a 5 kilogram ball traveling east at 0.98, collides with a 6 kilogram stationary ball. We'll call this one number 1, call this one number 2. Immediately afterwards, the lighter one, that's number 1, travels 0.6 at 50 degrees north of east. Here's the heavier one, 38 degrees south of east. Is it elastic or inelastic? Hey, do they stick together? No. If they stuck together, we know 100% for sure it is, what is it? Inelastic. But they don't. So if you got 30 seconds left on your test, and I'm correcting the test, and you're on this last question, and you got to bubble in elastic or inelastic, what are you going to bubble in? It's probably going to be inelastic. We don't want to do that, but if we have to, that's what we're going to guess, inelastic. What we want to do is calculate for this one the initial kinetic energy and the final kinetic energy. So let's do that now. The initial kinetic energy, 1/2 of 5 times, oh no, it's traveling east. Okay, that's good. 0.98 plus, this one's stationary, right? That's easy, isn't it? Let's calculate that initial kinetic energy. We find that it is 2.4 joules to 2 significant digits, right? Let's calculate EKF. 1/2 m1v1f squared plus 1/2 m2 v2f squared, all right? 1/2 of 5 times, this is the troublesome thing here, 0.6 at 50 degrees north of east. What do I do with that? X and Y's? X and Y components? Nope. Why did I not do, like, why did I not pay any attention to the 50 degrees north of east or the 38 degrees south of east? Because it's a scalar, right? If I'm doing this using momentum, I got to pay attention to that. But if I'm doing this as kinetic energy, I don't. Makes it way easier. Solve for EKF there, by the way, into two significant figures again. It works out to be 2.1 joules. EKI is greater than EKF. Okay? If you lost kinetic energy, what is it? What is it? Somebody said it over here. Inelastic. If we had have guessed, would we have guessed correctly? Yep. Yeah, because we were going to guess inelastic, right? But you don't want to be right 9 times out of 10. You want to be right 10 times out of 10. So try to do it right. Try not to guess. Just guess if you have to. You've still got a pretty good chance. Good. All right, your homework over the weekend is worksheet number 5. Worksheet number 5. What you're going to do on worksheet number 5 is take some of the questions that you've already done on other worksheets, use the numbers that are in the question and answers that you've gotten for final velocities, and then determine whether they're elastic or inelastic. So don't recalculate the final velocities of these objects. You already have those answers, right? Just use the answers that you've gotten to calculate initial and final energy. Unless they stuck together. If they stuck together, then there's no guessing, right? We know that's inelastic if they stuck together. Okay.